So now part 2 of a complex analysis practice final exam, picking up with number 4. Let P of z equals z to the 5th plus 3z cubed plus 2z plus 7. Use Rouché's theorem to determine the number of zeros of P in the disk. Absolute value of z is less than 2, counting multiplicity. Then determine how many zeros lie in the absolute value of z is greater than 2. So argument principle problem. So P of z equals z to the 5th plus 3z cubed plus 2z plus 7. On absolute value of z equals 2, we're going to compare z to the 5th with 3z cubed plus 2z plus 7. Absolute value of z to the 5th is 32, and absolute value of 3z cubed plus 2z plus 7, that's less than or equal to 3 times the absolute value of z cubed plus 2 times the absolute value of z plus 7. So that will give us 24 plus 4 plus 7 equals 35. So this does not work. So instead we'll compare 3z cubed plus 7 with the rest. So on absolute value of z equals 2, absolute value of z to the 5th plus 2z is less than or equal to 32 plus 4 is 36, which is not smaller than absolute value of 3z cubed plus 7 necessarily. So using argument principle, Rouchet, with homotopy, P sub t of z equals z to the 5th plus t times the quantity 3z cubed plus 2z plus 7. And this is where 0 is less than or equal to t is less than or equal to 1. And a cleaner Rouchet choice, that's going to be with a homotopy. A cleaner Rouchet choice is on absolute value of z equals 2. Using z to the 5th plus 3z cubed against 2z plus 7. So on absolute value of z equals 2, absolute value of 2z plus 7 is less than or equal to 11. Also, absolute value of z to the 5th plus 3z cubed, that equals absolute value of z cubed times the absolute value of z squared plus 3. And since absolute value of z equals 2, absolute value of z cubed is 8. And this absolute value of z squared plus 3 is greater than or equal to 3 minus the absolute value of z squared. So that equals 3 minus 4, and that equals negative 1. And that's also not needed. So direct Rouchet comparison is not immediate. And observing the problem is borderline for a simple Rouchet estimate. So if we use the argument principle numerically or refine the contour, use the argument principle numerically or refine the contour. And using root count computation, all 5 zeros lie inside absolute value of z is less than 2. So 5 zeros lie inside absolute value of z is less than 2. 5 zeros lie in absolute value of z is less than 2, And since the polynomial has degree 5, no zeros are going to lie outside it. So zero zeros lie in absolute value of z is greater than 2. Now, just as an addendum to this, let's just go over this real quick. So that P of z is equal to z to the 5th plus 3z cubed plus 2z plus 7. If we factor that, that's z times z squared plus 1 times z squared plus 2 plus 7. And on absolute value of z, that equals 2. So absolute value of z times quantity z squared plus 1 times the quantity z squared plus 2. This absolute value is greater than or equal to 2 times quantity 4 minus 1 times the quantity 4 minus 2. So that's going to be 2 times 3 times 2 is 12, larger than 7. So by Rouchet, P has the same number of zeros as z times the quantity z squared plus 1 times the quantity z squared plus 5. So 5 zeros inside there, absolute value of z is less than 2, and 0 zeros lie in absolute value of z is greater than 2. Okay, so that is number 4. And now moving along to number 5. Let's see if this holds. Actually, let's just take these off. Put up number 5. So for number 5, we want to suppose that suppose F is meromorphic, and on the extended complex plane here, the Riemann sphere, with simple poles at z equals 1, 2, 3, and no other finite poles. So suppose the residue here, f at 1, that equals 2, and residue f2, that equals -5, and residue here, f at 3 equals 1. So part A, they want us to find the residue of f infinity. Part B, if f of z approaches 0 as z approaches infinity, what could you conclude about the coefficient of 1 over z and the Lorentz expansion of f at infinity? And part C, construct one example of such a meromorphic function. Okay, so meromorphic functions and residues. So part A here, for a meromorphic function on the Riemann sphere. Okay, so we have this over all in C hat of this residue f at A equals 0. So the finite residues are 2 plus -5 plus 1 equals -2. So this residue is going to equal 2. For part B, the residue at infinity is related to the Lorentz expansion at infinity by this residue here, f at infinity equals -a sub -1, where a sub -1 is a coefficient of 1 over z in the Lorentz expansion of f near infinity. So -a sub -1 equals 2, and a sub -1 equals -2. And for part C, they want us to construct an example of such a meromorphic function. So one example is going to be f of z equals 2 over z minus 1 minus 5 over z minus 2 plus 1 over z minus 3. And this has simple poles at 1, 2, and 3 with desired residues. And f of z here is asymptotic to 2 minus 5 plus 1 in the numerator divided by z. So that's equal to -2 over z. So that f of z goes to as z approaches infinity. So f of z equals 2 over z minus 1 minus 5 over z minus 2 plus 1 over z minus 3, and that would be a valid example. Okay, so, and now moving along to number 6. Number 6, we want to find the conformal map from the upper half plane here that we're given. So upper half plane here, and here we're given that h equals the set of z such that the imaginary part of z is greater than 0. Onto the horizontal strip here for the s w such that 0 is less than the imaginary w is less than pi. And then we want to modify the map so that z equals I is sent to w equals I pi over 2. So this is just a quick overview of this one. This is a conformal mapping problem for number 6. So a standard conformal map from the upper half plane to the horizontal strip is here. This w is going to equal the principal log. So that's for, I'll just use this notation, the principal log here of z, which indicates a specific branch, where the principal log is the principal logarithm on h. And if z equals re to the I theta, with 0 is less than theta is less than pi, then the principal log z equals log r plus I theta. So we're going to get 0 is less than the imaginary component of that principal log z less than pi. And therefore w equals that principal log z, maps conformally onto S equaling the set here of w such that you have that 0 is less than that imaginary w less than pi, imaginary parts of w less than pi. And here, the principal here, log I, equals I pi over 2. So this map already sends that there, that I maps to I pi over 2 here. And the required map here is that W equals the principal log of Z. Okay, so that's all for part 2. Thank you very much. Have a great day.